Again, the presentation was great, great project, guys and girls. All right, so for the final exam, the exam will cover chapter 6 through 10. And I am not going to be posting, review guide. However, I have a 3-page that we can kind of go through, in class together, just to give you an idea how the exam will be. So, I assume everyone can see my screen, right?
Yes.
Okay, thank you. All right, so the exam will be from chapter 6 through chapter 10. So chapter 6 will be about preparing the preparing to model your data. And there you may have, few of these, questions. One, so what's first, you might be asked to explain the difference between supervised and unsupervised method when it comes to machine learning, right? What are the two? What's the difference between the two? And I think we said one has a target, variable, and the other does not. That's the primary difference. Uh, and which, data mining tags are associated with supervised methods and also unsupervised method and also both, right? So this question is kind of loaded. So first, you have to give the difference between the two. What's the difference between supervised and unsupervised machine learning? Then once you have that, once you've done that, um, you also want to list, the tags. So we talk about data mining tags in chapter 6, and what are those, some of those tags, or what are the tags associated with supervised machine learning and unsupervised machine learning. And once you specify that, you know, there are some tags that can be used in both methods. You also want to specify those tags that are used in both methods. So next is to describe the differences between the training data set, the test data set, and your validation data set. Like what's the difference? What are the differences between those? So there you have 3 different data sets. So uh, again, we say when you are given your a problem, and based on the algorithm that you choose, you have to split your data set, into training and testing. And we said the test data set is also referred to as the holdout. So the holdout data set, because that's why you hold, you keep away from the training, process. And once you train your algorithm, then you use the test, data set. And the validation is also, validation data set can also be used to validate your model. Then another question here is, should we strive for the highest possible accuracy of the training in the data set? And if yes, why? If no, why not? And then how, about the validation set. And this is about accuracy. So, uh, well, instead of being just going on, I mean, you guys want to answer number three, any ideas? Should we strive for the highest possible accuracy of the training set? Yes or no? And if so, why or why not? I mean, it's review, right? So, uh, I believe we shouldn't because, yeah, so Martin is saying we shouldn't because it might create a bias and the training set will rely, there will be much reliance on that. So, yeah, so maximizing the accuracy, we shouldn't, right? So, because if we maximize the accuracy of the data model against the training set, that will lead to um, overly complex model. And once we have that, then we turn to shift into overfitting. So this will introduce a problem of overfitting. So in this case, the model will tend to memorize details of the training set, which is not good. And there will be no generalization, to test and validate the model. So that's why we don't really want to do that, because doing so will lead into overfitting. So the optimal level of the model complexity, is achieved. And if you look there, I think there's a slide in chapter 6 where we talk about um, the model, right? I mean, the optimal level of complexity that we want to achieve. Because once we go to the left of that model, then that will lead to underfitting. And if we underfit a lot, then our model could starve, from not having enough data. And if we push too far with the accuracy, then we overfit. And the problem of memorizing, trying to memorize the training data set, could be uh, an issue. So I think there was an example where we mentioned, if you're trying to do some analysis on like the salary, you're trying to classify income. And if you overfit your model, and let's say we have within the training set, an employee, individual called David, and David has a salary of maybe 85K. And if the model sees any name called David, with once we have this overfitting issue, then it will turn to wrongly classify in a record with the name David. So that's the reason why we don't want to do that. Uh, so explain why we sometimes need to balance the data. I mean, that should be fairly straightforward, right? So why do we need to balance the data? And that kind of leads into question number 5. So if you know the reason why we need to balance, then question number 5, speaks to the reason why. So the training data set um, is balanced so that we can have sufficient number of common and also, as well as less common classifications to occur within a data set. So if we don't have enough training data set, our classification might not accurately, perform the classification, or our algorithm might not accurately perform the classification. So therefore, we need to balance the training data set. So that leads to question 5. Suppose we are running a fraud classification model with a training data set of 10,000 records, and of which 600 of those 10,000 records are fraudulent records. So how many fraudulent records need to be resampled if we would take the proportion of the fraudulent records in a balanced data set to be 20. So in chapter 6, there was a formula we used to calculate this, and this is exactly from one of the slides in chapter 6, except that we changed the numbers. So if we want to resample the data to comprise 20% of the training set, then we will have to leverage the following equation, where we know the total number of fraudulent records will be 600 plus x. We don't know what's x. X is what we're trying to sample, right? That's what we're going to solve for. We say it's equal to 20%. It's going to be 20%. That's 0.20 times the number of records that we have, which is 10,000, minus, sorry, plus, because we're trying to add, because 600, just imagine we have 10,000 records that we have. And from the training data set, and only 600 of those are fraudulent. So we don't have a good representation, a sample, to train our model. So that's why we have to resample here. And this is a formula, that we use to do the resampling. So you can then solve the above equation, and this will be something close to 600 plus x equals, when you multiply that, you have 2000 plus 0.20x. So you just need to, go ahead and complete that and then solve for x. So the answer that you will get for x, is what, that will be the number of records that we need to resample. So, and again, you can just reference, there's a, and this question will be there actually. The numbers will be different too. You're not going to see the exact number here. So, um, should we, or should the test data set be balanced? Yes or no? Okay, well, since there's no answer to that, then I'll make sure this will be on the exam. And if yes, why? And if no, why not? I mean, so what do you guys think? Should it be balanced on? Uh, no, because it's supposed to be about random. That's exactly right. So the test data set should never be balanced. The test data set represents real world data and should be evaluated as is. So that's good. Thank you. Uh, then that will be chapter 6. So chapter 6, you have questions, from These are the areas that you should focus on in chapter 6. Then chapter 7 would be about the k-nearest algorithm. So it says clearly describe what's meant by classification. Um, so we know classification is a type of predictive modeling, where the target variable is a categorical variable having a predefined finite, set of possible outcomes or classes. And the objective of classification model is to classify each new observation, determining which class each new observation belongs to. So that's the reason. That's what classification is all about. Then, so chapter 7 would be two questions, or one of these two questions. Discuss the advantages and disadvantages or drawbacks of using a small value versus a large value for k. So we say the k-nearest algorithm, right? Um, we have k. So what k really means, and what's the advantages or disadvantages of or drawbacks of using a small or large value of k? Uh, so choosing the optimal value for k is most likely not to be obvious and may require several attempts. So if you choose a small value for k, then the model will be unduly influenced by outliers or noise that may lead to overfitting. So that's if you choose a small value for k, then that could lead to overfitting, right? Where you could have um, unduly influence um, results because of outliers. And however, if you were to choose a larger value for k, then the model is less likely to be influenced by noise. But it may cause your model to completely overlook, extreme conditions or rare conditions, generalizing the new observations to the larger mainstream of classes. So that's the advantages and disadvantages. So smaller k value, you increase um, your accuracy, but by doing so, then if you have an outlier, that could really throw off and even possibly lead to overfitting. So chapter 8 is for decision trees. We said describe the possible situations when no further splits can be made at a decision node. And we talk about these, right? So we mentioned the leaf node. Um, so we say all branches of the decision tree terminate at the pure leaf nodes. No additional splits are required at the pure leaf node. So in this case, all records, contained at each leaf node have reached or we have the same, target class value. So termination can occur at a pure leaf node or um, one or more branches may terminate at a diverse leaf node. So, just make sure you know the difference, between the two. So whenever there's termination, it can be at a pure leaf node or at a diverse leaf node. So what's diverse, what's pure, diverse? I mean, pure is where you have just one outcome, right? And when it's diverse, um, you have multiple. So next, we suppose that our target variable is a continuous, variable. So it's continuous and it's numeric. continuous numeric, can we apply decision tree directly to classify it? You know, if so, if well, we cannot, right? So how can we work around this? So to use a continuous target variable for classification, we first we have to discretize it. So we have to change it into discrete, variable. And this process takes a range of values and convert them into discrete categories. So again, if you revisit the slides, you will see examples, of that. So here, here's a true or false. So decision trees seek to form leaf nodes to maximize um, how heterogeneous they are, right? So here we're looking at, so to answer this, you have to understand what's the goal of decision tree. Is it for, homogeneous, nodes coming together, or heterogeneous node? What are we trying to maximize here? So that's a true or false. So, and then anybody wants to guess, to answer that? Not guess actually, but to answer that question. Okay, we see true, we see false. All right, so it's false actually. So decision trees algorithm attempt to create leaf nodes that are as pure as possible. And this occurs when a leaf node contains the maximum number of records with the same target class value. So this results in high confidence and increased classification accuracy. So we don't want heterogeneous, right? That's not what we want. Instead, we want, pure. So we want to really reduce it, not to maximize, you know, different, values. So for chapter 9, neural networks, what's the sole function, of the nodes in the input layer? So you have the input layer, right? So the nodes in the input layer, they are there to accept the data from the input variables. The data values are passed directly to the nodes in the heading layer. So the only reason that you have the input layer is it's like a hub. So, and if you look in chapter 9, you'll see the diagram, right, where you have the input. You have the data coming in, and when they come in, they come through the input layer, and nothing is done really. So all the input layer does is to accept the data from the input variables and pass that data directly to the nodes in the heading layer. So should we prefer a large heading layer or a small one? Describe the benefit and drawbacks of each. So the the more heading layer you have, the more accurate. So it's the same question, going back to overfitting or underfitting. So if you have more heading layer, you increase the accuracy of your algorithm. But that also could lead into overfitting. So you need to find the optimal point, like deciding how many heading layers you're going to have in your algorithm. So describe how neural networks, function non-linearly. Again, you can get that directly, uh, from the slide. So it's a combination function, right? So we have a combination function. that computes a scalar value from a linear combination of node inputs and connection weights. And this value, this scalar value, is an input in it's an input to the activation function. So we talk about the sigmoid, the sigma function, and this function produces an output that is not necessarily linear related to its input. And that's how it happens really. So it's merely done through this activation function or through the sigmoid function. Then here we have a true or false also. Neural networks are valuable because of their capacity for always finding the global minimum of the sum square of error, right? True or false. So all neural network models are not guaranteed to find the global minimum of the SSE. However, the algorithm will find the local minimum that often represents a good solution to the problem at hand. So the learning rate and the momentum parameters are often adjusted to search for to search the local minimum, for near performer. For near optimal solutions. So the neural network, the model is not guaranteed to find a global minimum of the SSE. However, the algorithm will find a local minimum, of the local minimum that represents a good solution to the problem that we're trying to solve. So with that said, I will let you, answer that whether it's true or false. Uh, and that will be it for chapter 9. Then we start to get into chapter 10. Chapter 10 is about hierarchical, and CABE means clustering. So the first question there would be to describe the goal of all clustering algorithms or all clustering methods. What's the goal? And then we emphasize this in class, right? I mean, you have the in between cluster, within and between. So there's so the primary objective of clustering is to divide the entire data set into relatively homogeneous subgroups. And these subgroups are referred to as our clusters, such that similarity of observations within the cluster is maximized and similarity, at the same time, similarity of observations between clusters um, is minimized. So that's the primary reason of all clustering methods. Uh, then next question here we say suppose that you have the following data, right? It's a single variable in one dimension using the single linkage method or approach. So we want to use a single linkage method to identify the clusters. So this is something we've done in class. So we have the single linkage and we have the complete linkage. So, but here's the data set. We have this data set. How will you proceed? About doing this. So keep in mind the single linkage approach. Um, the focus there is the shortest distance, right? And the complete linkage is looking at the farthest apart. So the single linkage is looking about the nearest, apart. Nearest, and the complete linkage is looking at the farthest apart. So, so step one, always, you want to measure your steps, and you say step one So in step one, we say all 10 observations are placed in their own cluster. So all 10 observations. So that's always going to be the case. Then step two, so in so doing, that means we're going to have all these 10. Will be placed in their own cluster like that. Okay, that's all you have. That's step one. Then step two, the algorithm is going to search the distance it's going to search the distance matrix for the closest two clusters, and then it's going to merge them. And if we look at the shortest, um, it's going to be 0, right? So the distance between. So what's going to happen here is we, step two, and this might not just be with step two alone. So what we're going to do is we will look for the first shortest distance will be 0. So if we look here, we can see that we have 0. Let me change the color for this. So we have 0, and then we have 1 and 1. And the reason for that is the distance between 1 and 1 is 0, and the distance between 3 and 3 is 0. But we also have the distance between 9 and 9 is 0. So this will be step 1, step 2, and step 3, right? So uh, so we can say step 1, step 2, 3, and 4. So this will be step 2, step 3, because step 1, we've already grouped them together here. So then in step 2, we can group 1 and 1. Then we move to step 3. And once we group 1 and 1, then we can group 3 and 3. And keep in mind, this will be repeating. That will be repeated there. And then we remove that. So that's how it's going to be. But what we can do here is instead of doing this, we can actually group. So this will be step 3. And then step 4, we can do 9 and 9. So what we can do is we can group step 2, 3, and 4 together. And we can do that and say, okay, so we have that. That's step 3. And then step 4, we group those together. So you guys have the get the idea now, right? Okay, for those 2 questions, would there be partial credit for question? Uh, well, yes, there will be partial credit for question. And keep in mind, though, I mean, you're doing this from home, right? So, and we're kind of going through this together before the actual exam. And it's not going to be the exact numbers, but, I will do, I'll make some changes. And not all questions will be on the exam. So this is a master, like a superset, and the actual exam will be a subset. And so for these 2 questions, yes, you should format your answer similar to this, right? And again, you can also look at the example that we have. So I think the example kind of goes through that. So we don't want this method, so we can put, step 3, 4, and 5 together. Then we have that. Uh, And then next will be step 5. So in step 5, our next step, we've done 0. So the next one is going to be 1. So we can take this, and 1 is going to be the difference. It's going to be 6 and 7, right? That's 1, because it cannot be two. 6 and 7, that's 1. But, well, actually, so let's say this is step 5, and we also have the difference here is 1. So we can say step 5 and step 6 and combine this. So because we know the difference 0 to 1 is 1, and 7, 6 and 7, the difference is 1. But we also have another one. So that means we can say step 7, because we have the distance between 9 and 10 is 1. So that means step 5, 6, and 7 will yield this. Then we move to the next one, step. So we just did 0, 1. So the next one now is 2. So we see there's a difference from here is 2. And we also see a difference from 7, 7 and 9 is 2. So that means we're going to have step 8 and step 9 will yield this, because we're looking at 2. So that's what we have. So then we move to the next level, step 10. And so we came from 2, now we go to 3. So if we look, of course, 3 and 6, the difference between there is 3. So we can say in step 10, we merge, we form a cluster here. And this will be the end because every variable, yeah, every value has been accounted for. So once we reach this point, that's going to be it. So the algorithm searches the distance matrix, that's close to everything, and this will be the end of our single, linkage. So, and the next question says, suppose we have the same data set, right? But we want to do this using the complete linkage. What will be our approach? So our approach would be the farthest apart instead of um, the closest. So any questions? I'm not going to do this one. I'm not going to give the answer to that, but using this as an example and knowing the difference between the single linkage and the complete linkage, I think you can solve this. So that brings us to another question here. We say answer the following questions to the best of your ability. And each answer is worth, 10 points. So this will be for section 2. So section 2 will be, 30 points, or could be 20 points if, we choose to just give you 2 questions, or it could just be 20 points if we choose to have just 1 question. So we say given a data set, uh, this should be to the right. We say assume that we are using the k-nearest algorithm or k-nearest neighbor, classifier that uses simple voting. And again, if you have question on this, so we discussed the simple voting or the weighted vote, right? Where the vote, when there's a tie, they have to vote, and which vote has more weight than the other. So that's the weighted voting. But here they're using, our classifier is going to be using simple voting, where a new data point is given the class label of the highest number of its nearest neighbor. So what you are asked to do here is to classify the points. X is 250 and Y is 150 with a K value of 3, 5, and 10. So this means you're going to do this 3 times. The first time you do it, the K will be set to 3. And then the next round, you change K from 3 to 5. And next round, you change K from 5 to 10. Then, describe how you reach your answer. Any question on this question? Is it really clear, well understood? So in answering this, what I expect, you will say if K equals to 3, that's the first thing you want to do. The new point, so we already have this cluster. This is what we have. Let me. So this is what we have here, and we have the x, axis running, and then vertically we have our y, axis. So, and the points that we're trying to classify is where x is 250 and y is 150. So that will bring us x is 250 here and y is 150. So that means right here. So this is a point. We're going to have a point here. But once we place this point, how do we classify this point? So if we look on this graph, we have plus the stars and then the minus, right? So those are the three types of symbols that we have. But if we introduce this new point that's going to be placed right there, how are we going to classify this point? If we have our k to be set to 3, would this be classified as a hyphen or a star? So let me see. Let's say here's our new point. Yep, that's our new point right there, because we're saying x is 250 and y is 150. So we have the new point there. So, and if we have k set to 3, our new point, x equals 250 and y equals 150. It'll be classified according to the classification, according to the k equals 3, because that's what we said. We want to change k to be 3. Then after that, what if we change k to be 5 and then change k to be 10? So if k is 3, then our new point will be classified according to the classification of the k equals 3 points closest to. So k, the classification will be this new point will be the 3 points are closest to it. That's going to be our classification. So then we know 2 of these. So we see 2 of those points. They are a dash, right? That's what we see. So let me change that color. And one point is, so we have 2 of the points are halfens, right? And one of the points um, is a star. And that's all we see here. So looking at this, we can see closest, because k is 3. So we're going to take the 3 neighbors, the 3 closest neighbor, right? So halfen and halfen. So the 3 will be 1, 2, and 3. And because we are using the simple voting method, that means we have 2 halfens. So therefore, there's no point will be classified as a halfen. So it will be a dash right there. That's that would be our classification. So our reasoning, um, and because we know, and one of the point is that. So and the only reason for this that we're doing voting is because now we have two, right? So um, based on voting would, so does that make sense? I need some feedback, folks, so we can try to get out of here. So Matthew is saying, so for this, we would redo the formula 3 times for k value. Yes, you have to do this 3 times for k value. So that's one. Then I will also come and say if, it's not like formula, but you have to explain, right? You have to do that 3 times. So say if, that's one. If k equals 5, now I changed my k to 5, but keep in mind, we still have the same point, right? So that our new, if k is 5 and our new point, so I'll repeat this, the same thing. K is 5, the new point, that's what we have, would be classified and, according to whatever, here. Let me just, so this will be the same, except that's going to be it. And that means since k is 5 and we have our new point is going to be here. This is our new point. So first we took 3, 1, 2, 3, but this time around we have 5. So of course, it means that's the first 3 that we had, right? So we're going to keep those 3. But this time around we have 2 extra that we need to take into consideration. Well, from this point, I think this one seems to be closer. So that will be taken into consideration. And another closer one, to me, from this point, will be this one. So those will be the extra 2 points that we have. So now we're going to have, this will be our cluster, right? I mean, right there. But I mean, those will be the points that we need to take into consideration. But in so doing, uh, now we can further say we have 2 stars and 3 half-ins, right? 3 half-ins. So again, using the same logic that uh, we have 3 of those are going to be half-ins, and then 2 would be the 2 asterisks that we have. And since 3 of the 5 closest point, is a manus or a half-in, the classification would therefore choose the half-in. Does that make sense? Okay, good. And you'll do the same for 10, So you have 10, K is 10, and you have to go back and just go through whatever we just went through. So that will be it. So in this case, we're going to have, you will have 1, 2, 3, and star, star. So that's basically it. And then when you have your K is set to 10, what's going to happen? You do that and you make your conclusion. Uh, so what's about this? Given the following decision tree, classify the following records, according um, accordingly, right? Whether the customer will buy a computer or not. So here we have a decision tree. So, and this is student. So we say the variable, we say if the student um, or the person, we a customer is trying to buy a computer. And the first thing we check the age of the customer. Is the customer's age greater than or equal to 30? I mean, sorry, if the age is less than or equal to 30, or is the age between 30 and 40? If the age is between 30 and 40, then we say yes, they will purchase a computer. But if the customer is above, or below 30, if they're below 30 or equal to 30, we don't make a decision there, right? So because it is not a leaf node at that point, but instead it's a decision. So we have to also check to see if the customer is a student. And if the customer is a student, then we say yes. If yes, they're a student, then the decision or the leaf node says yes, the customer is going to purchase a computer. But if they are less than 30 and they are not a student, then they are not going to purchase a computer. So that's exactly what you have. These are the scenarios. So student, no. And a credit rating, good. Age equals 25. What's going to be the outcome for this? Will the customer purchase or not? And all we want here, for answers would be, you can put that right in, parentheses. So what's about number B? Will the customer purchase or not? Okay, since I'm getting no feedback, I'm just going to stop right here and say, and give you read the other questions for you instead of me trying to answer other questions for you guys. So this will be A. The customer will not purchase it because you have to follow the decision tree. Student, no. So they are not a student, and age is 25. But in so doing, first we have to look at the age because that's the beginning of the tree. So age is less than 30, yes. Student, no. So they are not going to purchase. So credit rating is not taken into consideration here because the only time we take credit rating into account is if the customer is over 40 years old. But if not, then we don't even see this branch. So because of that, the customer will not purchase a computer and based on this decision tree. And for the second, say age 32, so 32, that's going to be here. So they're aged between 30 and 40. And automatically, it means yes, they will purchase a computer, because of their age. Thank you. Thanks, Edwin. Thanks, Josh, and Rachel too. So for C, it would be yes. That's exactly right. So for C, yes. For C, yes, they will purchase a computer. And so this will go on. You might see up to F or G. So I might give different scenarios, but this is just an example, right? So one more question here. We said given the following silhouette plot, what can you say about the cluster result? What will you recommend as a next step in clustering this data set? And we saw this in one of the presentations. So here's a silhouette plot. So what can you say about this, right? And so given this, um, we said the average silhouette width is 0.58. How do you determine the average? Again, I'll say reference your notes. Um, with an ideal width, the goal is the closer we get to one, the better, right? That's what we want. So, um, suggestion in this case suggest performing clustering and do the silhouette plot again. Where the number of clusters, is either 4 or 6, uh, and that's going to be based on an average. So first, you first have to do the average. Again, this is directly from the slide. So, and that will be it. Those are the things that we will cover for the exam. And I just want to stress again: be very careful. Pay attention to questions where you have multiple parts. Like here, right? So whenever you see multiple parts, make sure you answer all. You address all the parts. Any questions? All right. If no questions, sorry for keeping you guys over time. All right. Thank you, too, John. Thanks so much, class. Again, I just want to repeat. Um, I just want to repeat. I appreciate everyone for this semester, knowing that when we started the semester, this is not what we anticipated.